Good morning, everyone. Welcome to today's webinar hosted by SOLIDWORKS. Today's call is titled Getting Started with Computational Fluid Dynamics. Easier said, CFD, as we know it. So welcome to today's call. I was thinking about this call yesterday, actually, as I was stuck in traffic, and I'm sure you've all experienced being stuck in traffic. That wasn't my plan yesterday, but unfortunately my flight home got canceled. Had to get on to one that was just an hour later and ended up in full traffic coming home. And as I was doing that, I use Google Maps, right? So I'm sure a lot of you use these types of tools to get around. I do very much because I'm traveling in cities where I have no idea where I'm going. So obviously very useful there. But even when I get home and I don't know what traffic looks like and where there may be problems, I use it to try and help me find the best path, right? The best flow to get home. And as I'm going through and there's all this traffic, there's ways of getting home, because this is home, that I know that the tool doesn't necessarily show me or doesn't necessarily try for me because it's just not in its regular path. So I think I'm smarter than the tool and I try these paths and I end up in more traffic because there's construction that I did not know about that's all of a sudden there and a road is closed and I end up somewhere worse. So I end up back on a path that it had originally suggested to me, and I end up getting home 20 minutes later than it had even predicted. So I'm frustrated on traffic. I'm frustrated at the tool for not giving me the right info. I'm frustrated at the tool for not giving me all the paths possible and all the different flows possible for getting home, not giving me enough options and enough solutions for me to have the best idea of where I'm going. So this is kind of the same thing that you're living with your products today, whether it's water, whether it's air, particles, whatever's flowing through your product. What you're looking for is the best path to get the result that you want. And obviously what I wanted was to get home as quickly as possible. So thank God that we have better tools and there's better solutions out there than Google Maps to simulate computational fluid dynamics, so CFD. And this is what we're going to illustrate for you today. Now, before we kick into this, I'm going to just give you a few logistics. On the right panel side of the GoToMeeting window, you've got some downloads, some documents that you can download. And right below that is a chat area where you can write any questions that you have. We're going to address these during or at the end of the call, depending on how this goes. And if for some reason this goes full time, then we have a record of who's written these questions, and we'll definitely get back to you to get you your answers, because we want to make sure that you're getting the most out of this information. So I'll introduce myself. I'm Joelle Guenette. I am the Territory Manager for Eastern Canada. Hosting this call for Eastern Region, US and Canada today, which is great. And I've got some people on the call. I will introduce Joe in just a few minutes, but Michel Cloutier also with me, who's a territory or a technical manager for SOLIDWORKS, who hosts all of these calls with me. And you may have seen him if you've or heard of him if you've gotten on these calls with me. Or of course, as we visit customers across our territories, we hear from a lot of you. And one thing that we have heard many times from companies who have started using simulation tools for CFD, the one thing that we hear about is the surprise that they have on the results that they get, right? They said, I really thought that putting a fan here or putting a heat sink here or whatever it is that they're doing or designing my product this way would get me the results that I wanted. And we went to manufacturing with it, and lo and behold, they get some simulation tools, try it on just to confirm what they thought, and they get completely different results. And this is where it becomes an eye-opener, where you see what really happens, where the air is not at all going over the products that you're looking to cool, or the water is not going anywhere near where it's supposed to, or circulating back on itself where it shouldn't have. So all of these things is what we're trying to avoid, and simulation is there to guide you, give you some direction, let you be more innovative in what you're doing, because it gives you more confidence in your product, and of course get you a better quality result at the end of the day. So that's the main goal of doing simulation before you go to manufacturing, so that you have confidence in what you're doing. To present this today for us is Joe Galliera. So as you see here, we have nicknamed him internally at Dassault Systems SolidWorks Flow Joe, because this is what he does, this is what he eats for breakfast, this is what he lives. So he is the perfect person to share this information with us today. His experience comes from the aerospace world, in simulation, of course. That's where he focused his time, and he's been with SolidWorks for almost 17 years now, focusing exclusively on simulation products, and sharing this the story and meeting with customers and helping them get to the solutions that they want, with great tools and great solutions. And with that, I will hand it over to Joe, and I will be back at the end to close this off with a few more notes. So Joe, over to you.
All right, thank you, Joelle. I really connected with your traffic story, because in school, when you're studying fluid dynamics, it's very complicated equations that you're dealing with, and one of the things you can do and simplify down to a 1D calculation or 1D flow is traffic. So we actually study traffic with fluid dynamics as well. All right, so I think Joelle already introduced me, so let's get into the presentation. And first, I'm just going to introduce what the capabilities of flow simulation are, because you probably have an interest in knowing what we can do. And probably I could say confidently we can solve about 80% of all types of flow problems that are out there that you would want to solve. We can do internal as well as external flow, so you'll see 2 of those cases today, 1 for each. And we can run the gamut between laminar, transitional, and turbulent flow, whether it be subsonic, transonic, or supersonic. And one of the great tools in using flow simulation or any CFD is in heat transfer, because the temperature affects the fluid properties and pressures and velocities, so it's very intertwined. There's 3 conservation methods which are solved using this Navier-Stokes solver: conservation of mass, momentum, and energy, and then you have your state equations of the fluid. So all of those are incorporated in this tool. So heat transfer, electronics, cooling, and what have you. More on that later, actually for another webinar, but just wanted to mention that that's a key use of the tool. We can do rotating components, incompressible as well as compressible flow, all different types of fluids, whether it be Newtonian or non-Newtonian. The results that we calculate don't stand on their own. We can take pressures and or temperatures and thermal heat coefficients and export those to our FEA solution, SolidWorks simulation, which then you could find out like how much a part deforms due to the pressures, or do the thermal analysis as I mentioned. We can do transient as well as steady state and free surfaces, which is a really nice capability as well. And to really take advantage of the parametric nature of SolidWorks, as everything is embedded in the SolidWorks interface, we can drive those parameters to get an optimal design. So we'll see some of that as well. And then in terms of e-drawings is a great way of communicating and sharing information with others who may not even have SolidWorks, and that still is true with flow simulation. You can send the results over to them and have them comment and send it back to you. We do a nice exchange of data with our ECAD solutions, right? So that's another great use of taking a design that you have and then doing a thermal analysis on that. That's another key thing. And sound, acoustic, power levels, those would be, something that you may be interested in as well. Then we have two add-ons. I'm just going to just quickly mention them: electronics cooling and HVAC. That is for the next webinar in just a couple days in the future this month. All right, so and what I was going to say is I mentioned up front in the slide that 80% of all problems we can solve. It's probably easier to say things that we can't handle, such as for hypersonic flow. That's just because of the Navier-Stokes equations, break down at that high velocity where particles start or flow. The fluid starts looking like particles rather than continuous flow. So that's a limitation with a solver and what have you. We don't do chemical reactions. And in terms of, we do rotating bodies and sliding rotation, but we can't have a moving mesh translational to the part. So those are just some examples of things that the software doesn't handle. But like I said, for most problems, and maybe for your company, all of 100% of what you need, we offer. So I'm going to try to capture some of these capabilities with two examples. The first one is this external aerodynamic problem, and we're going to look at how we can calculate perhaps the drag of an athlete running down the field. And I wanted to just thank one of our customers, Falcon Pursuit, for this model. They create very complex, high fidelity geometry such as this human body. And the reason why I chose it is it's interesting problem and has some very complex geometries such as like the fingers and ears, and it's very detailed. And so you can see just the quality of how we can do that in our software. So you can see here I'm over into the SOLIDWORKS interface, and to start out a new problem, in your SOLIDWORKS interface, there's a tab, and you would need to have flow simulation added into that. And when you do that, in addition to in your feature manager, you have this flow tab, which does that. So you can go back and forth between the flow project and your model and anything else. If you want to work with configurations, we do honor those. That would be in the next example. I'll show a little bit more about that. But you can definitely work all and change a model if you needed to or had that purpose. So, and when you start a new analysis, there's a couple ways, and the first way that I'll explore this is with the wizard tool up here in the toolbar. All right, and this is a standard practice of what you would start with when you're doing a new problem from scratch if you haven't run it before. So we're just going to go through here, and let me zoom in to each and hit each one of these setup tools, and then it'll set up the problem, and we'll get into making some boundary conditions and what have you in the setup. So the first thing we're dealt with is the units. So we have our predefined base units like Imperial, IPS, SI units. And if I scroll through here, you can see that I have several other units. These are all user-defined units within there. Now, everything is solved in the background in SI, so you have consistent unit system. But for the user, how he interacts with it, it's very flexible. So instead of pressure being pascals, which is I'm going to use this PZ, and I kind of like that. And you can see the conversion. I like that for this application, and the conversion is just 1/1000th of a Pascal. So we're going to get very small. It's nicer. I like enjoying using this one better. In terms of velocity, right? I was thinking about this. What is the best unit to use? And then I was thinking about how fast a footballer might run down the field, and we measure this fields and yards, and usually they have this 40-yard dash that they can do. So I know then what speed that players can run in yards per second. All right. And we can set the temperature to Celsius, geometrical considerations, and loads and motions actually is what I want to go to here, for our forces and such. So we're going to do gram force and things like that. Now we can create a new unit system on the fly, just making some modifications to the name. And what I'm going to do is actually just to make sure that I have everything changed. You know, I prefer to use millimeters instead of meters and things like that. I'm just going to use this one that I've already created in that manner. Clicking on here, we go to the physics of what we are going to solve. And this is an external flow problem. We can add other types of physics, as you can see here. Time dependency is a really nice way of solving an external flow problem, but I don't have the time to get into that all right now. But just for your curiosity, if you have a time-dependent transient problem, if you want to change the load, such as a heat load or velocity or an angle of something parametrically, you can do that over time. So that opens up a lot of possibilities that you can do there. But just real simply, this is an external flow problem. And we'll move on to our fluids, and I'll add air and my fluid here. With gases, we can add humidity into the air if that was important. And I'll use this opportunity to click on New, which will bring up our engineering library. And just to show you that this, you can create multiple different types of fluids or other settings such as solid materials and things like that, all here within the library. So if air, all right, and we take a look at the properties of air real quick, the dynamic viscosity, as you would expect for a part, is all temperature dependent properties, right? But let's just say, for example, there's a case where you wanted to have air and set it at a specific properties. You can just come in here and you can see that I had defined this a constant viscosity here, and you can just type in the value in the units that you desire. So you can save that and then recall that fluid here in any one of the user-defined fluids. Same thing with the units. When I saved it, it went into that library. These are defining conditions for what is the roughness. Now, there's no clothing on the athlete, but let's just say you could add some texture and roughness. And this is a default value when you're setting it up in the wizard. And you get into the interface, you can set up specific surfaces with a different roughness. But we'll just assume that the athlete has normal roughness, if you will. And then we can set up our ambient conditions. For a transient study, this would be the same thing as an initial condition. So we can set these as the temperature outside. I'll put 22 degrees C, nice warm day outside. And then for our velocity, so for an external flow problem, many times you want to define the flow that the air in this case is moving. And we're going to define this not by vectors, but through an aerodynamic angle, all right? And I'll put in the velocity of the air. Let me zoom in real quick. It to be, I determine athletes that can run 40 yards in about 5 seconds. Actually less. The top athletes can run less than 5 seconds. But let's just say in a real situation, rather than a test, they can run about 8 yards per second. So we can put that in. That's set up like that. Okay. And then for the plane, so we can take a look at our coordinate system here, X, Y. So I'm going to set up my plane in the Y, Z, and then my angle in the Y, angle of attack here would be 0. And we can confirm this angle by this arrow which is shown on the screen. So this athlete is running in the Y direction, and And then when I finish the wizard, you can see that there's this box that is created around the athlete. So the software doesn't know exactly the whole domain that we want to run it in. So we're going to inform it very easily. So this is something you have to do typically for an external flow problem, but for internal flow problems, I'll show you that you don't typically have to change that. But we're going to set the computational domain here by right-clicking, and I'm going to go to a view of the top view, and I can just slide this arrow all the way down, and then it gives you the opportunity of changing that value here in a flag if you wanted to. So I'll make that 6 meters. And so you can see that by doing that, it sets that up, makes a change here. So however you want to do the input, you can change that and then change the other direction. This is in the X direction. All right, so we can slide it like that. Now, if you want to, do the inputs over here, we'll put 1,000, or what is 1 meter, and in this Y direction that the guy is moving, we'll put 1,500. In the Z direction, we'll change our view. And so the ground is going to be easy. We're going to set this one at 0. And because we want to simulate like the athlete is running on the ground, what we're going to do is we're going to actually put in a symmetry constraint. So that is a condition that sets that the fluid is moving at the same speed on either side of this. So that really actually simulates, without defining a wall, the ground moving. And then the height here, we can just scale that down to something that looks good, and then put in the value here for 2 meters. So this is setting up our entire domain for where we're going to be doing the calculation. We hit OK, and then we can move on. I'm going to just real quickly, since I'm done with this coordinate system, I'm going to right-click and hide that coordinate system for the flow simulation. And I can hide this computational domain as well. All right, so we've already basically set up the flow, the boundary conditions that we wanted to do, so we can just skip over that. Let me talk a little bit about the tree. This tree is customizable. You can customize it for how you might want to use it, and I have most of the options turned on because I'm working with a wide variety of customers that are doing different things. So you can see some fans and heat sources and porous media and things like that. But what I want to do for this study is focus on goals at first. So we can input global goals, so that's everywhere within the computational domain, goals at a specific point, on a surface, within a volume. Like I use this all the time for defining what the temperature of a component is, and then we can define an equation goal. So let me set a global goal here. And you can see all the different types of parameters that we can define. And I'm going to scroll down to our forces in the X, Y, and Z direction. All right, when I hit OK, then I'm just going to rename these. So F of X, this is the side force. All right, F of Y, and this is just good practice, is my drag force. And then F of Z is our vertical. I'm not going to put lift, but you can imagine that that would also be lift in this case, all right? So I can add all of those goals in one step. And then if we wanted to find an equation goal, we can specify the drag coefficient this way, or actually I'm going to define CD times A, because I could find out the projected area of the athlete, but that might take a little bit more time. So I'm going to just define this by clicking on that one goal, defining the force actually divided by 1/2 times the density and the velocity squared. So this is 8 yards per second squared. Now, I'm simplifying this, and actually I could refer back to some input data of my general settings of my initial condition of the velocity. Right, so if I were to change that velocity, it would update with it, and then square that. And this should be in, yeah, it's already finished up that end parentheses. So if I change that velocity, it'll update it. Now, in truth, that the unit is in yards per second, so actually I would probably want to define some. That's one of the things, if you want to make sure everything is consistent in the units, that it all works out, they all cancel out, because this unit is actually non-dimensional. By clicking N, I can change that to no unit, and clicking on OK and run that. The next and final thing we're going to do for this setup is define our global mesh settings. So a little bit on this is that we have automated mesh settings, and you can see that by turning on an option, I can visualize what the basic mesh is. So this is going to just capturing the computational domain, and I can slide this bar, and it further refines it down further and further, as you can see. So level 3 is a default. Typically, I like to choose myself around 4, and then you can specify specific gap sizes and wall thicknesses, which are, and I'll put in a 1/4 inch here, or let's just use 6 millimeters. So this can define for the software where important small features might be, and it'll cut the mesh down to that size at least, all right? But we're not limited to just automatic meshing, right? We can also do and define the mesh number of cells in a given direction. You can see that changing on the screen on the graphic area, or we can define the mesh size here by typing in a value of the unit. So you can see how that affects that one there. But for most, even for a seasoned user like myself, the automatic mesher does work quite well. Let me zoom out of this. And one of the things that it does, for example, is you can define the lengthening them by defining some value in order to lengthen them further down in the computational domain. Now, there might be an area around the athlete that I want to refine the mesh, and we can define a local mesh just by right-clicking on a mesh and defining that. There's 2 different options, either defining it based on a reference of a geometry that exists, or in this region, I'm going to define a primitive type of cube in which I'm going to specify that. So just like the computational domain, I can resize this, and this is just going to be a local mesh around the athlete a certain distance away, and then I think that looks fine, and then I just want to make sure I get the height. And then with this, then I can specify which type of cells, such as the interface between fluid and solid, to refine, as well as small geometry, curvature within the body. You know, if there's a cell which is covering greater than 20 degrees, then I can capture that, refining it a certain number of times and setting it like this. So it gives you more control over how that is done, all right? And lastly, before I solve, I'm just going to introduce the ability to do refinement meshing. So we can specify in the global domain some meshing refinement and the maximum number of cells maybe that you want to achieve, not to go beyond that with the global mesh size, all right? And then we can solve this problem. Now, I already have a project solved, and let me pull up the results and I can show you some ways to create results here. So since we were first focusing on the mesh, maybe I'll show you a plot of the mesh let me do this cut plot here. So this is a good view of the velocities in yards per second that this athlete is running. I think in this case I put in 5 yards per second for the velocity, but I intended to do that because I wanted to show you a way that you can vary that with one method called cloning. All right. So in addition to this cut plot, we can do things like add vectors to it. So this, you can show the vector. Also, this can be changed anywhere within the 3D space that we have. And this is another view type that I really like, is streamlines, to be able to visualize that. All right, so that's generated, and a really nice way to show the results as well is with flow trajectories. So let me, with these arrow types, we can get a nice visualization and animate that flow. And then we can go ahead and capture this, save it out as an animation, as a AVI or MP4 file type, and capture this and what have you. And as well as I mentioned, you can save this out as an e-drawing type. Now, so this is for one setup. I wanted to introduce this ability to, if you want to take a look at variations on this, you can utilize this function to clone a project. Just like that athlete, maybe he's really a great athlete, we would want to clone him. But we can copy the results, and if you have a configuration that you want to then switch to it, you can specify which configuration that you want to choose, or you can create a new configuration. If you're going to change the geometry, maybe putting on some clothes or helmet or what have you, you can define it like that, and then add that to your simulation. So that copies everything down to the, all the setup and what have you. And when you solve this type of problem, you can solve this using a batch run. As you can see here, you can specify which studies to solve, which ones to mesh, and also you can specify how many CPUs or how many projects to run simultaneously if you have enough horsepower on your computer there. So these two setups, the first one that I set up with you, and then the cloned study. And also, if you had multiple projects or assemblies opened, then you could create that. So what did we learn from this external aerodynamics? How we use the wizard to start up a new study, how we can manipulate units and create new projects using the engineering library, setting up the computational domain, the ways we can do global and local meshing, creating goals such as global goals as well as equation goals, some of the result plots, and cloning studies, and using a batch run for that. So the next study we're going to look at is doing a CV calculation on a globe valve. So this is an internal flow type, and we're going to see how we can utilize flow simulation to solve this real-world type of problem. All right, so with this setup, we could do the same thing with the wizard if we were going to start the problem from scratch, but I wanted to introduce a new way of doing it, is creating a new project from a template. All right, so the default template type is internal water. That's just the default out of the box, but you have the ability to, with, say, a project is, let me do this. So if I activate it, and then I can create that template directly from the project setup. So let's just say an expert, a trained user of the tool was able to set up a problem for specific types of problems that your company is frequently doing, right? Then you can hand this off to many people within your design team and enable them to run safety calculations using the flow simulation tool without having intimate knowledge of how to work with the software. Just some cursory training would be enough for them to go through that. So I'm going to start this calculation with, I'll call it test 2, using a template. So with the template, you have the inlet volume flow defined, the outlet pressure, and all your goals and mesh settings and refinement, all the things, the steps that I went through in doing that. Now, maybe for this webinar, it might be good to just go through these boundary conditions and how you would insert a new boundary condition. All right, so you just choose some geometry, and utilizing the SOLIDWORKS select other, you can select a face, so that would be that inlet face. All right, in the preparation of the model, all I needed to do was add some geometry on the inlet and outlet sides in order for it to be a watertight solid. I'll show you that just after I get through this boundary conditions dialog box and showing you what's going on here. So we can define inlet and outlet mass flow, volume flow, velocity types. We can do pressure conditions as well as wall conditions, whether setting a wall temperature, roughness, as I mentioned before, wall motion. You can specify some of that, again, just as long as it's not changing or needing to change the mesh, so you can't have it translate into the fluid volume. So in this case, we can specify a volume flow rate of a specific gallons per minute, which is set up and needed for this type of CV calculation. So 175 gallons per minute is the way we set that up. And then on the other side, if we just show these call outs, we just have ambient, this is 14.7 PSI, which is the proper unit again for doing this calculation. Now, as I mentioned, the setup of the problem is very important, okay? So let me do a cut section view here so you can see a little bit more of the internals. Now, so what a requirement for setting up a problem like this is to have it closely related to how the physical test setup would be done, okay? So when you're doing a valve, you need to have a length of pipe at the inlet on the upstream side, and then on the downstream side, you need a certain length of pipe where you're going to be calculating the pressure or measuring the pressure, right? So the way that this is defined by ANSI test standards is that you have 6 diameters downstream from the outlet of the valve. So this length of pipe is defining that. And then let me take a look at the solid bodies in here. So we have the exit pipe and the inlet pipe. As you can see, it's highlighted, the inlet pipe on this side of the view. And then we have these inlet lids. So the lids are just capping off what would be the opening there. So let me just show you, what this was previous to that is just how it was presented, the opening as, we want the flow to move through that. And just very simply, you can add a geometry, a simple extrusion from a converted sketch of that pipe diameter and just extrude that out very easily. and then that very easily caps it off and makes it watertight. Now, by making it watertight, then the software is able to automatically identify where the fluid region is. So this is a check geometry tool, and I'm going to choose to have it calculate what the flow volume is. So you can see here from the geometry, we know the SOLIDWORKS geometry very well, and it's just capturing that and visualizing it here. If there was some issue with the geometry, perhaps, or there was an open boundary that it wasn't closed off, it's going to tell us that the fluid volume here is 0, and it may give you some geometry issues. But typically, geometry issues are rare. You know, it happens. You know, if parts are interfering with one another, that's not a problem. We can handle it. We're just looking at the open volume, if you will. Where it becomes a problem is that, like, if you have a line that's touching like a surface, so it's only a line. So what it's essentially doing in the background is creating a Boolean of this to extract that fluid volume. If it's not able to do that, then it might cause some geometry issues. So we just try to avoid that when possible. And then for this calculation, I have one other part that is hidden here, it's body. And essentially, let me make these inlet faces pipes transparent. So essentially, this is the other part of where we want to do the pressure tap, right? So we're looking for a region which is just 2 diameters upstream of the flow, where we can measure the pressure there. And we can do that with introducing a geometry in SOLIDWORKS, but through a component control, we can deactivate that, right? So that it allows flow to move through it, but then I can use the surfaces to select on those and use those as a surface for a goal, okay? So that's another goal type that we can define. And let me just go through real quick from scratch, and I'll set up this problem from a wizard just so you can see the process of me going through this. So this is an internal flow type. Water is our default fluid, as I mentioned before. And we don't need to set anything here other than the temperature of the water should be at 59 degrees F or 15 degrees Celsius. All right, so we can specify that there. The computational domain, we'll hide that. We'll hide this coordinate system. Insert the required volume flow. And I'm specifying this 175 gallons US per minute is to ensure just that we have a Reynolds number of about 100,000. The boundary condition on the outlet side is going to be a pressure. And we'll keep that default value like that. The component control, I'm just going to specify and turn that off. And then I can go down to my goals, insert surface goals at this case. And the first one we're going to select is this one here. So we're going to define the average static pressure. And we already know we're defining the outlet pressure, so we don't need to utilize that. And then we can define an equation goal just like I showed you last time, but this time we're going to use a boundary condition as our outlet. And this is our delta P using pressure as the unit. And then we can define the another equation goal using that delta P in order to calculate the CV. So off the top of my head, it's 1/2. You know what? I'll show you. I'm going to cheat by showing you another way of doing this. I can delete these. If I go to my test 2, and if I already have some setups here, I can control select, copy this over to my new project that I'm working on, like so. So all of those are just copied from the previous one. I set up my global mesh setting here. And calculation control options to add some refinement. So I'm not going to add any local mesh refinement, and I'll use, say, 1.5 million. And we're going to set up a table refinements at a certain number of iterations. This happens to be like so. And then I can hit run. Now, this is for, if we take a look at this section here, this is for a specific fully open condition, okay? Now, you can see that I have this parametric study set up for this fully open. How can we set up a parametric study for something where if we want to set up for a configuration rather than cloning it and defining it to a new a configuration and then solving as a batch run, we can actually set up a custom built batch run with a parametric study. So we can go through doing a quarter open, and this is all run through a parameter in the model that is just driving the height of this piston here when you're screwing it up and down. So all of that is just done through a configuration that we have. Let me do it like this. If I double click this part, it'll reveal the dimensions, and then just by changing this value here, I'll make it 1.6, for example. And you can see how that updates the geometry. So all I want to do is to essentially drive this through a parametric study. And the way that we do that is just click on this icon to add that in. There's different types of studies that we can do. Right now, I'm going to be doing a Whatif analysis type. There's a goal optimization, which you can have the software change that. If you're looking for a specific CV value, for example, you could have it change the height of that until it reaches that goal. Or you can use a optimization technique that uses a design of experiments approach. So these are two different algorithms. The goal optimization is just like a seek and find, where the DOE has a specific algorithm for that. But the Whatif analysis type is probably the most straightforward, and with it we can either change a simulation parameter such as the velocity or pressure or other conditions like that. But I'm going to add a dimensional parameter. And I'm just going to add this by selecting it from here, just as I showed you before. So this is that fully open 3.65 inches. All right. And this is specifying it as right now discrete values. So I can come in here and edit this and add more discrete values in this. But there's other different types of defining this. Range with a number, like so from minimum to maximum, a step, around, or there's a range with a step. So I'm just going to do a number here from, I'm going to put in, divide that by 4. So I'll do quarter open, half open, 3/4, and then fully open. So that represents all of those cases over here. Now that you can see that that's specified with all those values, we're going to add our output parameters that we want to add. So I'm going to add all of our goals to there. And then that sets up this, as I mentioned, a customized batch mode. So what it's going to do is solve, not simultaneous, one after the other, each of these design points with the specified dimension that is changing, and that's going to fill in all the values of the question marks, what those are. All right, and then once we have our goals, we can then export that and evaluate it with different tables and summaries and things like that. So let me show you for this fully open study here that I have. I'm going to open up this Whatif analysis, and we're going to evaluate these calculations that we had done. Okay, so you can take a look at each of these design points as I had just set up before, and then the CV value and all the other goals that I had specified in my setup of this. Then we can summarize this as a table of values. We can take a look at a history of how those calculated. We can compare them using a delta value, and we can highlight values which are greater or less. Red is greater, blue is the least. And I do like this bar chart. You can do a line chart or a bar chart for these values and then export that to an Excel spreadsheet. So the Excel spreadsheet is a built-in template, so there's nothing fancy that I did. This is out of the box capability that it just dumps that data into here and then creates this value of CV, which then you can manipulate the Excel file just as you would like to do and that you're familiar with. All right, what did we learn from this hydrodynamic problem? The importance of matching the physical test setup to get good results. I started this problem from a template and how that can be utilized to expand it to other users who may not be expert users of the flow simulation. I defined some equation goals, and using an equation in another equation. I showed you how to do parametric studies in the Whatif type and exporting that out to an Excel spreadsheet. I just wanted to highlight a few other types of analysis that this tool is ideal for. That just today I decided, since I'm going to be focusing on those in the next webinar, I won't show a thermal analysis, but we have a great functionality with that, both internal as well as external flow. In this mobile phone example, it's doing both types, so you can combine. That's actually being done as an external flow problem, but it just includes internal flow. Transient analysis of heating up of this valve of hot oil, showing plot types of how heat escapes from a plot, and we can do many different sizes of flow, from small components to a large data center, different scales. And other applications, pressure drop in a car. This is a transient aero problem of a wing profile, 2D analysis we can do, as well as this building doing HVAC cooling application. There are handouts that we're going to make available. So if you take a look on the right-hand side of your screen in the GoToWebinar interface, and if that's not open, use the orange arrow at the top to show your panel like this. So using that orange arrow, and then open up the section for handouts, and then you can click on those in order to download each one of these 3 different handouts that we're making available. One is a flow simulation buyer's guide, why you would choose flow simulation. The second is gives you an overview of the software, and then a more specific one just for simulation tools in SOLIDWORKS in general. So I think they'll mention this and remind you about it. There's a link that they'll show you that you can use that to register for the next webinar. But this is going to be on our 2 add-on modules that I briefly mentioned, the electronics cooling module, and then the HVAC as well for environmental and ASHRAE parameters and things like that. So I'll close there, and I'll hand the ball back to Joelle and Michelle and see if maybe I'll take a look at if we have some questions in the meantime.
Are there any questions? All right, thank you, Joe. So much great information. I don't know about you, everyone on the call, but I feel like I need to go for a run now. Feeling like I need to exercise after seeing that simulation. So great information. Of course, there's so many different application and variations of what can be done with this type of solution tool. We're giving you some examples that obviously Joe finds interesting and enables him to show you different aspects of what can be done within this, but every one of your scenarios and your situations is unique. If you need to see this again, to see the information, you can go to this is recorded, so you can take a snapshot of this QR code. You can also go back to the link that you received to join this call. That will bring you back to the registration as well, and you can share it with others. All they have to do is register for it. But instead of giving them a link to how to get on, it will bring them right to the recording. So please don't hesitate, share this information. Our next webinar, also hosted by Joe Galliera, Flow Joe, as he mentioned. Here's the QR code for it. If you have not registered for it, you can do so using this, or back to the invitation email that you may have received. We're going to focus specifically on HVAC and the electronic cooling modules, so 2 different modules that SOLIDWORKS offers to work in conjunction with the CFD or simulation flow tool that we offer. Give you more advanced information on those very specific applications that are mentioned in the module's name. So that will be June 17th. It is a Monday. It's not our normal day for doing webinars. But obviously Joe is in great demand, and we take him when we get him. So it will be on a Monday, and hopefully you can join us if that's what you require. If you want more help, you want to look at this very specifically for you, you can reach out to any of us. You can, of course, reach out to your reseller if you know who that is. Your reseller will probably reach out to you anyways to see, is there anything else that we can do for you? Is there any interest in this from a company perspective? What can we do to help you have a better confidence in your product, or help you with innovation in your product? Because that's what we want to do at the end of the day. So I don't think we have time for questions. We're already past the hour. Maybe if there was anything real quick, Joe, is there anything you wanted to address?
No, I think you're right. We don't have time for questions.
Don't have time. No. If there's anything in there, we can get back to you, or we can share the questions with your reseller, and they can address them with you. So many ways where we can get to your questions if you did ask some during the webinar. Thank you for your time. Thank you for spending this hour with us. We appreciate it. We hope to see you on the next one for HVAC and electronic cooling modules for SimFlow. Have a great day, everyone, and thank you, Joe, for all this great information. We really appreciate it, and we'll see you as well on the next webinar. Bye, everyone.